Howdy everyone, welcome back to our third and final part of our Chapter 5 thermochemistry discussion. We're now up to Hess's Law, which is another topic that we should have gotten in Chem 2. And so there's a couple different ways we can use it. We'll kind of review those ways. A lot of reactions we can get the delta H. We just have them. They're easy to measure. We can do it with the various calorimetries. But for a lot of reactions, for some others, it's not easy. What if it's all gases? How do we get gases into the calorimeter? How do we get some other things if we can't mix them together without them reacting immediately, but before we're ready for it? How do we measure these delta H's? And so if it's a very difficult one where you can't isolate specific chemicals or isolate a specific reaction, we're going to use Hess's Law to calculate delta H from previously published delta H's, from other enthalpy changes that we know. Right? So the basic idea here of Hess's Law, its definition, if a reaction is carried out in a series of steps, the delta H for the overall reaction is the sum of the enthalpy changes for all the individual steps. And this is because H, enthalpy, is a state function, right? H was based on E, which is a state function. It's based on P, pressure, which is a state function, and V, which is a state function. So because everything that goes into it is a state function, so is H. Remember, that just means it does not matter how you got there. So that means we can do the same thing here. The delta H will be the same regardless of how we got there. So for example, if we start with methane plus oxygen and we're burning them, if it goes directly to carbon dioxide gas and liquid water, it'll be a negative 890 kilojoule change. But if first it goes to carbon dioxide gas and water vapor, well, that's only going to be negative 802. But then if that water vapor condenses, that'll get us another 88. And then, okay, negative 802, negative 88, hey, that's the same negative 890. So it doesn't matter if it was one step or two steps or three or four or five. As long as you start in the same place and end in the same place, the overall change is going to be the same. That's what Hess's Law tells us. All right? Well, how can we use this? Well, we have something called the enthalpy of formation. This is what is the enthalpy change to make a compound from the elements. So the elements in general have a enthalpy of formation of 0 because it costs 0 energy to make an element from itself. But other compounds, some will be positive, some will be negative. It just all depends what it is and what it's made from. But it's just what is the enthalpy change to make it starting from just elements. And when we measure those, these are things that we've calculated carefully over time to get really good experimental data. We always try to get them at 25 degrees Celsius and 1 atmosphere of pressure. So if you remember gas laws from Chem 2, we had STP where it was always 0 Celsius and 1 atm. In thermochemistry, the standard conditions are usually 25 Celsius and 1 atm. So it's kind of an annoying thing when you see at standard conditions, like, well, which one are we talking about? That standard enthalpy is indicated by this little kind of degree sign, this naught up here. That tells you, oh, this is standard. This is 25 Celsius, 1 atm because of that little circle there. All right, so keep an eye out for it. You'll see it a lot. All right, and so here are just some examples. Like I said, some are positive, like acetylene. We got some very negative ones, like calcium carbonate, sodium carbonate. Right, some of the ionic ones are very, very negative because they're very, very stable to form. We have some positive ones here, benzene, acetylene. Now here's a surprising one, diamond. It's pure carbon. And you probably say, well, wait a second. You just said elements are 0. The most stable element is usually 0. Many elements have what we call allotropes, right? The different forms. And so remember from organic and Chem 2, carbon has graphite, it has diamond, it has fullerenes, it has nanotubes. Graphite is the most stable, so carbon graphite is the 0 one. Diamond is actually slightly less stable, well, just 1.88 kilojoules per mole, but it's slightly less thermodynamically stable. But these tables are in the book there in 5.3. There's also an appendix in the back. I think it's H, maybe it's G, but we'll look at it when we need it. But there's a big appendix in the back with many, many, many more compounds that we'll need to look up at some point. All right, so how do we use these to figure out a delta H using Hess's law? So say we're trying to do this one, the combustion of propane. So propane plus 5 oxygen makes 3 carbon dioxide and 4 waters. Notice that the water is liquid here, so we have to pay attention to that. And so we're going to kind of make a cycle. What we're trying to figure out is right here, from reactants to products. And pretend that this negative 2220 was not there yet. So what we're saying is, well, what if we can't go directly there? We could use our heats of formation to say, oh, let's take that propane and oxygen and split it up to the elements. To say, what would it be to go to just carbon, hydrogen, and oxygen? Okay? And then, so that's step one. Just decompose into the elements, because here's where we could use our delta H of formation. Step two, let's form some carbon dioxide. We have 3 carbons, we have a bunch of oxygen. Let's take 3 of them and make 3 carbon dioxide, as it says here. Okay, we have a delta H for that, right? There's a delta H for step 1, there's a delta H for step 2. If we have then a delta H for step 3, let's make some water. So the 4 hydrogens and the 2 oxygens, they combine to make 4 waters. We have a delta H for that. So we have 1, 2, and 3 for our delta H's. Well, Hess's law says if we add them all up, down, down, that overall change will equal from starting right here, and going right here. All right, so we have our 3 steps combined, well, or 3 steps written out, so now we combine them, and we can see here, hey, wait a second, my 3 graphites are going to cancel out with those 3 graphites. These 4 hydrogens will cross out with those 4 hydrogens. Let's see, what oxygens, are oxygens good? Well, I have 3 oxygens here on the left, 2 on the left. Since they're both on the left, they'll combine into 5 oxygens, right? So we can see what crosses out, what combines, and we'd say, yes, does that double check, does it add up to the reaction we want? Yes. Propane plus oxygen goes to carbon dioxide and water. So then if we added up these 3 reactions, we just need to add up the 3 delta H's. So that's where it says we're going to use Hess's law, that all the product ones minus all the reactants ones with stoichiometry, we can do that. So here we go. We had 3 carbon dioxides in the products. So we take that number that we'd look up on the table, multiply it by 3. We had 4 waters on the products. So we look up the liquid water number, multiply that by 4. So that's going to be combined because those are our products. We then on the reactant side, we have 1 propane. So we have the propane number, which is the 103.85 times 1. Then we have the oxygen number, which is 0 times 5. All right, now they've just distributed out everything in the second line. Then they combine. We'd say, okay, these 2 together, because they're products, that's negative 2,332.7. We have our reactants, okay? And then we're going to do products minus reactants, just like we said before. And there we get negative 2219.9, and well, I guess they rounded there because they wanted to. But yeah, that's the same number. So it didn't matter how we did it. Hess's law would also be, now here they did just straight from the overall reaction here, but we could also do step by step. So like I said here, we could take this reaction, which is plus 103.85. We could then add this second reaction, which is negative 1181, and then add the third reaction, negative 1143. If you add those all up and keep track of your signs, you would also get negative 2,220. So either way, it's fine. Okay? So we'll be doing that. This will be the majority for what we'll do here, where we look up the heats of formation from the appendix there, where we'll just kind of plug it into products minus reactants. All right, last one is about bond enthalpy. So this is sort of like reactants minus products, but it gets a little bit flipped around because we have to remember it always takes energy to break a bond, and we always get energy back out, released, when we form a bond. And for the same 2 atoms, it'll be the same energy, just opposite signs for breaking versus formation of a bond. Well, bond enthalpy is the definition is the energy, the enthalpy associated with breaking 1 mole of a bond in the gas phase. Everything's going to technically be gas phase here, even if it's not. Pretend it's gas phase, right? But it's always breaking. So bond enthalpies are always a positive number. And so here this looks like chlorine. If we break it, there's a certain amount of energy there. Here's methane, CH4. We're going to have to break 4 of those bonds. All right. So bond enthalpy is always positive because energy is required to break it. Energy is always released when a bond forms. And then here's one. The greater the bond enthalpy, the stronger the bond. This actually tells us if we have a very large bond enthalpy, it's probably that bond is not going to be very reactive. That bond's going to stay like it is. And so if we look at like nitrogen, N2, it's all in the air, but it hardly does anything. It just sits there. A lot of chemists will use it as an inert gas in experiments. They'll fill a chamber full of nitrogen. Well, why? Because it's got a triple bond, an incredibly strong, great bond enthalpy, a very large bond enthalpy. And so because of that, that triple bond doesn't get broken. N2 stays together and does not react. So you can kind of make some ideas of, will this bond break more likely or not based on, and react more likely or not based on how large this bond enthalpy number is. So if we look here at our definitions, right, CH, those bonds don't break very much because, well, it's 413. Same thing with carbon single bonds and double bonds. For some reason I thought triple bond was on here somewhere, but I'm not seeing it. Carbon-oxygen double bond, nearly 800. That one's not going to react very much at all or get broken. They don't give me my nitrogen triple bond here anywhere, do they? Or maybe it's on the next page. No. But it's usually around 800 or 900, if I'm trying to remember correctly. But N triple bond, I think, is 800 plus. The oxygen double bond. Now, it's not to say that's not reactive. We know oxygen's very reactive for other reasons, but we can kind of make an estimate based on it. So like these ones with very low enthalpies, the OF bond, OCl, these tend to be more reactive and easier to break. All right, so when we want to figure out the delta H of a reaction based solely on the bonds, what if we weren't given the delta H's of formation? You figure out all the bonds that are broken, and you figure out all the bonds that are made. And so because these are all positive, this is where I'm saying it's a little bit different. We're breaking the bonds and taking that amount of energy, and then we're going to subtract all the bonds that were made. So here it's sort of reactants minus products, but only because we're looking at the bond enthalpy is always the positive number. I always like to just make two columns and then just do a subtraction instead of trying to do an equation like this. I will just say, tell me everything that broke, and I will add up all those numbers. And then tell me everything that formed, and I'll add up all those numbers. And then, yeah, how much broke minus how much formed, there's our estimated delta H. It won't be exact because, again, these are all officially in the gas phase. And we said, well, phases matter. Liquid versus solid makes a difference. But they should be close to the other values that we'd actually get in an experiment. So if we're looking at this one, the formation of methyl chloride plus hydrochloric acid or hydrogen chloride, we'd say, okay, we've got to break a chlorine single bond, and we've got to break 4 CH single bonds. And, oh, I'm sorry, we only have to break 1. Let's say it again. We only break 1. So always look between reactant and product and say, well, what's my difference, right? It's a spot the difference. So I look here, well, 3 of the H's are still there. Only 1 of them goes away. So we break 1 carbon-hydrogen single bond. We also do break the chlorine-chlorine single bond. We will then say, okay, what bonds are we making? Well, we're going to make a carbon-chlorine single bond, and we're going to make a hydrogen-chlorine single bond. So those are the numbers I'm going to need to add up. So I'll look up the table here. If I go back, breaking a chlorine single bond, where is that? There it is. So we're up about 242. We're going to break carbon-hydrogen, so that's about, what are we up to, 655. So we're going to go up 655 kilojoules per mole. But then we got to form carbon-chlorine, so that's 328. We're going to form hydrogen-chlorine, which is 431. Well, those two numbers together, what is that, 61, or no, 59, I'm sorry. So 759. Well, if I'm going up 655 but going down 759, I'm going to release energy. That reaction is going to be exothermic, as they drew it here, because more energy comes out breaking or forming those two bonds than energy had to go in to break the other two. All right. So we're going to do more practice with that in class, but that's the basics of bond enthalpy, where you can kind of estimate based on what broke and what formed. Here's how I can get my delta H. So I know this chapter was a long one. I know it's got a lot of confusing terms, a lot of confusing equations. We're going to do lots of practice with this stuff and kind of go at a slower pace for chapter 5. We're going to take some time because this stuff will come back in chapter 19. So we'll get the basics here. We'll focus on what we need to focus on, and then we'll come back and get some more advanced stuff at the end of the course. All right, so go ahead, have a nice day, and I will see you guys in class.